Hi class. In this video here, we're going to move into section 7.3 and talk about between dimensions. Can the dimensions of fractals, fall through the cracks? And what I mean by that is like we know, if something is two-dimensional or three-dimensional, we kind of understand those things. But what's between those? All right, and it's a little weird, but so to start, let's talk about dimensions. So you're not going to be shocked by the answers we're about to give to these questions. So it's like, what is something that is one-dimensional? That's a line, just a line. So, what is the simplest example of a two-dimensional object? It's just a square, okay? And what's an example of a three-dimensional object? It's just a cube. Okay, so it's not too tricky. It seems as though we have some reasonable notion of dimensionality, okay? If an object has length but no width or height, it's one-dimensional. That's a line. If it has length and width but no height, it's two-dimensional, like that filled-in square. And then if it has length, width, and height, then it's a three-dimensional object. And we all live in three-dimensional space, so we can understand the differences between these three. All right. Well, that is as long as we're considering only very, very simple shapes. But like, what about the coastline of Norway, which isn't so simple? All right. And so suppose we consider, as we tend to do in this chapter, objects of infinite intricacy. So for example, what is the dimension of the Koch curve? Okay, so you can see I have the picture here. This is the Koch curve that we've looked at. On the one hand, since it's basically made of one-dimensional line segments, right? Just each of these is a little line segment. It might seem to just have length, so it's reasonable to think it's one-dimensional. On the other hand, it has infinite many bends and corners. If we look at it, it's so incredibly jagged that we might call it fuzzy, like mold on stale bread. And it seemed to have some slight thickness. That is, perhaps it is two-dimensional. But wait, it cannot be two-dimensional since it's just lines. Yet it cannot be just one-dimensional since its infinite fuzziness seems to make up a bit of area. Okay, so it's a little weird. So what is the dimension of this Koch curve? And we're going to derive that. All right, so we gotta go back, all right, and talk about what is a dimension. All right, so a straight line is one-dimensional. All right. A filled-in square is two-dimensional. A solid cube is three-dimensional. Somehow we intuitively know these facts. The problem is that our intuition fails us when we look at infinite, something that at infinitely intricate. All right. Let's try to devise, without appealing to our intuition, a systematic means of determining the dimension of a line, the square, and a cube. Dimensions we already know. If we could accomplish this task, then perhaps we could apply the method to compute the dimensions of these more exotic objects, like this Koch curve. Okay, let's begin with the filled-in square. Suppose the length of each side is 1 by 1 by 1 by 1, okay? How many copies of the square can be assembled to produce a larger square? Okay, well, 4 will do, because if you look here, you could have, if I copy this 4, so this is what's important. I'm copying this or scaling it to get its double the size to scale it. Okay, to get it bigger, I need 4. Okay, or you could do 9 as well. Right? If we use 4 squares to big square, we notice that the new square is twice as long as the original one. So to make a square 2 times as large as the original, okay, that is if we set the scaling on a copy machine to print edges twice as long. So the scaling is 2. We need n number 4. Okay, scaling. So to scale it twice, we need 4 of the original squares to make a larger square. Okay. What if we consider a cube having size 1? So if you look here, here's a cube. All the sides are each equal to 1. How many copies of the cube, all right, could be used to build a cube, each whose sides are twice as long? Well, the answer is you'd actually require 8 cubes here, okay, to build a cube with edges 2 times as large as the first one. So so here, two-dimensional object, to build something twice as long, we needed 4. All right. Here we have a three-dimensional object. To build an object twice as large, okay, we need to go from 1 copy of it. All right, so to build it twice as large, we would need 8 of these cubes. All right, so if we have a three-dimensional photocopier, we would scale things by 2 to go up to the first cube, whose sides are 1 to be a larger cube, whose sides are 2. We need 8 cubes. So what's the pattern here? If you have a line, okay, it's one-dimensional, and you want to make it twice as big, okay, the number of copies you would need would be 2. So what you would do, look what you're doing. you're taking your scaling factor and raising it to the power of dimensions. If you have a square, two-dimensional, you want to scale it by 2. The number of copies needed to build would be 4. So you would take the scaling factor, raise it to the number of dimensions. 2 squared is 4. Now we have a cube. Cube is 3 dimensions. We want to double its size. We want to scale it by 2. The number of cubes you would need would be 8. So you take the scaling factor, raise it to the dimensions. That's the pattern, okay? So you could see here it is scaling factor raised to the dimensions is equal to the number of copies you would need. All right, what about if you want to go 3 times, okay? So look, I think it makes sense, right? Like in a one-dimensional, if you want to scale it by 3, you would just need 3 copies of it. But what about a square? So in 2 dimensions, okay? And I want to scale it, I want to make it 3 times as big. Well, it turns out I would need 9 squares, okay? Where does that 9 come from? I want to scale it by 3, raised to the number of dimensions. 3 squared is 9. So a cube, to make it 3 times as big, well, the dimension here is 3, okay? I want to scale it by 3. So you take the scaling factor, 3, and raise it to the dimension 3. You would need 27 cubes. Okay, so we've established a relationship here, okay? So the hypothesis about the relationship between the scaling factor and the number of copies needed to is confirmed. Raising the scaling factor to the power of the dimension gives us the number of copies needed to construct the larger scale version of the object. All right. So we have an object for which n copies can be assembled to construct a larger version, all right, of it that has been scaled by a factor of s. Okay. So we can now define the dimension, so dimension d, of the object to be the power to which we raise s to have it equal n. Okay, so what we've seen here is the scaling. So like if I want to scale a cube or let me start with a square. If I want to take a square and scale it by 3, you take the scaling factor, raise it to the dimension, and that gets you the number of the original objects that you need, how many of those you have to replicate. So it turns out you can now solve for dimensions very easily, okay? And we're going to use this. So this ln here, this stands for the natural log, all right? So the natural log is a simple button on your calculator, okay? From this, we can solve for the dimension d is equal to the natural log of n divided by the natural log of s, the scaling factor. So n is the number of copies, s is the scaling factor. So the dimension is the natural log of the number of objects divided by the natural log of whatever the scaling factor was. So like what exactly is going on here, okay? So it brings us back to what is the dimension of this Koch curve, okay? So how much do we have to scale the original Koch curve to enlarge it to the bigger one we just built? So like if we look at this, how many times do we have to enlarge this to get to this, okay? So the answer is we have to scale this to go from this to this. It's multiplying by 3, because if you look here, here's 1 base, 2 base, 3 base. So the scale is 3. Notice that if the original Koch curve has a horizontal length of 1, then our large version has a horizontal length of 3, okay? So thus we see that the scaling factor is indeed 3. So what is the dimension? Okay, so here's the next thing. I know the scaling factor is 3, okay? If I want to scale this Koch curve by 3, how many new Koch curves do we need? So look, here's 1. I'm going to need another one, 2, another one here, 3, 4. So to scale it by 3, I need 4 Koch curves, okay? So what is the dimension? The dimension is the natural log of the number of Koch curves, which is 4, divided by the natural log of the scaling, which is 3. And if you were to plug this in the calculator, what we'd say here is even, this Koch curve, the dimension, instead of a one-dimensional, two-dimensional, three-dimensional object, this fractal here has a dimension of 1.26185, would go on forever. So this is what we mean by the dimensions falling through the crack. It's not a one-dimensional object. It's not a two-dimensional object. It is a 1.26185 dimensional object. All right, let's talk about this. We'll end with some mindscapes here, okay? So let's try this one. At the right, we see a parallelogram. Okay, here's the first one. How many copies do you need to build a parallelogram that is twice as large? Okay. And then how many copies do you need to build one that is 3 times as large? Okay. Well, look, we're going to use this same formula that I have done here. We're looking for the number of copies, n. So it's scaling factor to the dimension. Okay. So to build one that is twice as large, I want to scale it by 2. And what is the dimension here? Okay. This is a two-dimensional object. So it would be 2 to 2. The second power, we would need 4 parallelograms. Okay. How many copies do you need to build one 3 times as large? So I want to scale it by 3. The dimension is 2. 3 squared, I would need 9 parallelograms. Now let's take a look at this one. Moving on up. All right. Here's a triangle right here, along with some larger versions. What is the scaling factor for each of these larger copies? Okay. So I want to figure out what the scaling factor is. So I know the dimension of a triangle. Okay. It's a two-dimensional object. Okay. And then to go from here to here, there's 1, 2, 3, there's 4 triangles in here. So what do I have to raise to the second power to get 4? All right. This is a scaling factor of 2. 2, because 2 squared is equal to 4. This one over here, 1, 2, 3, 4, 5, 6, 7, 8. There's 9 triangles. So what is the scaling factor here of a two-dimensional object to need 9 triangles? Well, this would have to be 3 squared. So this one has a scaling factor of 3. All right, class. I know this was a quick video, and this is kind of like a higher level overview of what the chapter talks about. But as always, please read through the chapter to reinforce the object I've talked about. And let me know if you have any questions.